Hello, this is Dr. Christy Patton Lukes, a chemical engineering professor at Missouri S&T. This video series is for the course Introductory Transport Phenomena, a review based on the book by Welty, Rohrer, and Foster. We are looking at Chapter 1, Introduction to Momentum Transfer, and in particular, we are looking at the point-to-point variation of the properties in a fluid. And we will be specifically looking at pressure, although as the pressure changes, the other properties will change also. So the point-to-point variations in properties, we said that the pressure, for instance, would be the same in every direction, but it isn't the same at every point, right? The classic example that you should be able to, remember in your mind is barometric pressure, right? You hear a weatherman talking about how the barometric pressure is, changing, going up, going down, and that predicts weather patterns. You also, if you've ever traveled, you've experienced different pressure that may cause some inner ear problems or some other issues as you move from, say, down at sea level to up in a mountain. And so the pressure we know varies from point to point. We can write this, staying in a plane just because that's going to be easier. Any of this could be extended to higher dimensions or other geometries. But dP is going to vary with location x and y. So dP dx times dx plus dP dy times dy. Or we could introduce an arbitrary path through that space. So if you look at this curve here, ds, okay, then dp with respect to that curve is dp dx dx ds and dp dy dy ds. So this is turning this differential form into a derivative with respect to this arbitrary curve or path S. So you may or may not recall from when you took Calculus 3, but these dP dx and dP dy pieces, those are what we would term directional derivatives. So they're how the p varies in the directions x and y. Now we can use trig to convert the dx ds and dy ds terms to trigonometric functions of this angle alpha. Cosine is the adjacent over the hypotenuse. Sine is the opposite over the hypotenuse, and so therefore the cosine of alpha is dx ds, and sine of alpha is dy ds. So let's rewrite this in terms of the angle alpha. So let's look at this. Gives us dP ds is the partial derivative of p with respect to x times the cosine of alpha, or delta dx ds, plus the directional derivative of pressure with respect to y direction times sine of alpha, which was our dy ds. Now, we want to look at a couple of different paths to learn more about this. So first, let's look specifically at the path where dP ds is equal to 0. This gives us 0 is equal to dP dx cosine alpha plus dP dy sine of alpha. Now, sine and cosine can be combined. If I algebraically rearrange this to put one on each side and then divide both sides by cosine of alpha, we end up with the tangent of alpha is equal to negative dP dx over dP dy, or the directional derivative with respect to x divided by the directional derivative with respect to y. But we also know that tangent of alpha is going to be our dy dx. And this, of course, is all talking about the path where dP ds is equal to 0. So in order for this to be true, then it means that delta P is equal to 0, or P is a constant. What about the path where dp/ds is a maximum? If it's the maximum, then the derivative with respect to our angle alpha would be 0, or we can write that dd alpha of dp/ds is, okay, so if we took the derivative of cosine of alpha, we're going to get negative sine of alpha dp/dx. And if we take the derivative of the sine of alpha, we get cosine of alpha dp/dy. And that is equal to 0 at the minimum, or maximum, excuse me, in this case. So this is all going to be equal to 0. And again, I can play the same game. I can rearrange this algebraically so that I solve for tangent of alpha. In this case, I get tangent of alpha is dp/dy over dp/dx. Now, this is the negative reciprocal of what we just got a moment ago, right? Which means that this is perpendicular to the first case. Okay. Now, I also then can use this to say that the magnitude of the directional derivative at the maximum is. So dp/ds at the maximum is just our definition, dp/dx cosine of alpha plus dp/dy sine of alpha, where the alphas in this case, or the sine and cosine of alpha, are defined based on tangent of alpha is dp/dy dp/dx. Now here it's really helpful to recall a trig identity that is maybe not the most easily brought to mind, but you can look this one up if you're not sure. Cosine of alpha is 1 over the square root of 1 plus tangent squared of alpha. Well, tangent of alpha, we have said on this path, is dp/dy over dp/dx. So we'll just substitute that in to get cosine of alpha is 1 over the square root of 1 plus dp/dy over dp/dx squared. And then if I multiply through everything by dp/dx squared, or the square root of that, I get dp/dx over the square root of dp/dx squared plus dp/dy squared. Now, there's a very similar relationship. I'm going to very quickly write that down. Sine of alpha is tangent of alpha over the square root of 1 plus tan squared alpha. And for this path, substituting in tan alpha is dp/dy over dp/dx. We end up with dp/dy over the square root of dp/dx squared plus dp/dy squared. So very similar forms. One has dp/dx in the numerator, one has dp/dy in the numerator. So now let's take these and substitute these in to our definition of dp/ds max, this expression right here that we're looking at. So we're going to substitute these in. So dp/ds at the case where it is a maximum is going to be dp/dx over the square root of dp/dx squared plus dp/dy squared times dp/dx, right? This was all my sine of alpha, cosine of alpha, okay? And then dp/dy over the square root of dp/dx squared plus dp/dy squared times dp/dy. So I can now combine these to get dp/dx squared, and these to get dp/dy squared. So dp/dx squared plus dp/dy squared over the square root of that same expression means that dp/ds at the maximum case is the square root of dp/dx squared plus dp/dy squared. So that's going to be a useful result, but there's a vector form that will make this true. So if you recall from your Calculus 3 when we talked about gradients and del operators, okay, we can write this more efficiently in terms of vectors, and this is the magnitude of those vectors. The vector form that's going to satisfy both of the two cases we looked at is that the gradient of P, or sometimes we write that as grad of P, is the directional derivative in the x direction times the unit vector in the x direction plus the directional derivative in the y direction times the unit vector in the y direction. We also could use this as the del operator, and if we look at this in the traditional rectangular coordinates with 3D, the del operator is the derivative of whatever we're applying this operator to with respect to x times ex, the derivative with respect to y times ey, and the derivative with respect to z times ez. And so if we were to apply this to p, del p is the derivative of p with respect to x times ex plus dp dy times ey plus dp dz times ez. So again, it is the same as the gradient, but looking at all three directions in rectangular coordinates. Now we will also be looking at this in other coordinate systems as we progress throughout the course. This concludes our examination of looking at the variation point to point. We're going to look at the units that are traditionally used in the study of fluid mechanics or momentum transfer, and we're going to look at surface tension in our next video lesson. Thank you very much for your time.